Hello everyone, I am Dr. Manju Gupta, Department of Chemistry, St. Aloysius College, Jabalpur. Today I am going to explain different absorption shifts and effect of conjugation in UV visible spectrum. Lambda max is the value of wavelength at which a particular compound shows maximum absorption. And epsilon max is related with the intensity of the absorption band. By changing the structure of any molecule or by changing the solvent or medium of the substance, sometimes the value of lambda max and epsilon max may change. These changes are recorded as different shifts. These are known as absorption shifts in UV visible spectroscopy. There are 4 shifts. 2 are related with wavelength and 2 are related with molar extinction coefficient. Bathochromic shift or red shift, hypsochromic shift or blue shift, hyperchromic shift and hypochromic shift. First is bathochromic shift or red shift. When absorption maxima or the value of lambda max for a particular compound shifted towards the longer value of wavelength, then it is known as bathochromic shift. Since in the visible region, red color is present at the higher side of the wavelength. That's why it is known as red shift. The reason of shifting towards the longer wavelength can be the presence of any oxochromic group or by changing the solvent. First example, in case of benzene, benzene is a chromophoric group which shows absorption at 255 nanometer. The value of lambda max is 255 nanometer. When oxochromic group NH2 or OH, any one is attached, it shows lambda max value for aniline at 280 nanometer and for phenol 270 nanometer. So this is the example of bathochromic shift for pi to pi antibonding transitions. Similarly, in case of carbonyl compound, since carbonyl compound is polar, by changing the polarity of the solvent, pi to pi antibonding transition and N to pi antibonding transition, both type of transition can show bathochromic shift. So bathochromic shift when the value of lambda max shifted towards the higher value. Second is hypsochromic shift or blue shift. Hypsochromic shift is opposite to the bathochromic shift. When absorption maxima or value of lambda max for a particular compound shifted towards the lower value of wavelength or shorter wavelength, then it is known as hypsochromic shift. In visible spectroscopy, since blue color is present on the low wavelength value, that's why it is known as blue shift. Again, the reason of the hypsochromic shift can be the presence of oxochrome or change of the solvent. But another effect is due to the presence of a group which can remove the conjugation from the molecule. That means any particular group which can decrease the delocalization of the electron will decrease the value of lambda max. For example, aniline. Aniline in neutral solution shows lambda max, maximum absorption at 280 nanometer. When acid is added to the aniline, suppose HCl is added, aniline is converted into anilinium ion. In aniline, the lone pair of electrons present on the nitrogen, these lone pair of electrons are also in the conjugation with the 3 double bonds of the benzene ring. In case of acid medium, H plus ion can form bond with the lone pair of electron and convert it into anilinium ion. Now the lone pair of electron on the nitrogen atom are not remains free for the involvement in conjugation in the benzene ring. So there is the decrease in conjugation or removal of conjugation from aniline to anilinium ion. That's why in neutral medium, when in aniline NH2 group is as it is, then it shows maximum absorption at 280 nanometer, and in acidic medium NH2 group is converted into NH3 plus, aniline is converted into anilinium ion. In this condition, the value of absorption maxima or lambda max decreases to the 265 nanometer. So it is the example of hypsochromic shift where the value of lambda max decreases. These two shifts, bathochromic shift and hypsochromic shifts, related to the change of value of lambda max. Third is the hyperchromic shift. Hyperchromic shift is related with the alteration of absorption intensity or with the value of epsilon max or molar extinction coefficient. When the value of epsilon max for a particular compound increased, then it shows hyperchromic shift. Again, the reason of hyperchromic shift is maybe the presence of any oxochromic group. If oxochrome introduced to the compound, the intensity of absorption increases. In case of pyridine, for pyridine, the value of epsilon max is 2750. When in the pyridine at 2 position, methyl group is attached. Methyl group is an oxochromic group, and it has value of epsilon max is 3560. So on the introduction of CH3 group in the pyridine, the value of epsilon max increases. Another fourth shift is hypochromic shift. Hypochromic shift is again related with the change in absorption intensity. When absorption intensity or epsilon max value of a particular compound decreased, then it shows hypochromic shift. The reason of hypochromic shift is the presence of a group that shows distortion of geometry, as in the example biphenyl. The two biphenyl rings are arranged at coplanar with respect to each other. When in biphenyl at second position methyl group is present, it causes steric hindrance and the compound remains does not remains coplanar. That's why, and the geometry of the compound will distort it. So from biphenyl to 2-methyl biphenyl, the value of epsilon max decreases. For biphenyl, the value of epsilon max is 19,000, and for 2-methyl biphenyl, the value of epsilon max is 10,000. It is mainly related with the geometry of the molecule. This is the graphical representation of all four shifts. This is red shift, increase in the value of lambda max. Blue shift shows decrease in the value of lambda max. Hypochromic shift, decrease in the value of epsilon max, and hyperchromic shift, increase in the value of epsilon max. Next part is effect of conjugation on absorption spectrum. Conjugation means presence of alternate double bond in a molecule. Here, two molecular orbitals are shown. First is for 1-butene and second for 1,3-butadiene. In 1-butene, only one pi bond is present. For one pi bond, there are two corresponding molecular orbitals. pi and pi antibonding. In another words, we can say highest occupied molecular orbital and high energy orbital is lowest unoccupied molecular orbital. In the ground state, both the electrons are present in the ground state and they are paired, or they are present in the HOMO orbital. When one butene is irradiated with any electromagnetic radiation, the electrons present in the ground state level pi orbital, they absorb energy and transit to the higher energy orbital, that is LUMO, lowest unoccupied molecular orbital. The same orbital picture in case of 1,3-butadiene. 1,3-butadiene has 2 pi bonds. For 2 pi bonds, there are 2 pi bonds, pi bonding orbitals present in the ground state and 2 pi antibonding orbitals present in the excited state. Here the transition, only one transition is possible in case of 1-butene from pi to pi antibonding. Now, in case of 1,3-butadiene, in ground state, 2 orbitals, pi 1 and pi 2, in both the orbitals, 2 electrons are present. And in antibonding orbitals or high energy orbitals, 2 vacant orbitals are present. Which transition will be more probable? Pi 1 to pi 3, pi 1 to pi 4, pi 2 to pi 3, or pi 2 to pi 4. In that type of condition, always the transition from HOMO to LUMO is most probable. Highest occupied molecular orbital to lowest unoccupied molecular orbital. Out of the ground state energy, orbital which is having more energy to the transition orbitals of high energy which is having lower energy. Second condition, orbital which is of higher energy in ground state must occupy the orbital electrons. And second, in case of higher energy, the orbitals which are vacant must be of lower energy. Highest occupied molecular orbital to lowest unoccupied molecular orbital. Here you can see it is very clear that in case of 1-butene, the energy required for pi to pi antibonding transition is approximately just double as compared to energy required for 1,3-butadiene for transition from pi 2 to pi 3 or from HOMO to LUMO. The energy difference between the most probable transition is decreases. That's why the value of lambda max on going from 1-butene to 1,3-butadiene increases. It means as the conjugation increases, the value of lambda max shifted towards the higher value. These are the 3 examples: ethene, butadiene and hexatriene. In ethene, only 1 double bond is present. In 1,3-butadiene, 2 double bonds are conjugated. And in hexatriene, 3 double bonds are conjugated. Ethylene shows absorption at 174 nanometer. For 1,3-butadiene, the value of lambda max is 217 nanometer. And for 135 hexatriene, the value of lambda max is 258 nanometer. It means as the conjugation increases, the value of lambda max increases. This is another diagram which shows the energy difference decreases between the HOMO to LUMO as the number of conjugated double bonds increases. For ethene, it is maximum. For butadiene, it is less. And for hexatriene, it is very less. So from ethene to hexatriene, the value of lambda max increases. The absorbing group is same. Absorbing group is same, carbon-carbon double bond. Same type of transitions are involved, pi to pi antibonding transition. But only thing is that the difference in energy between the HOMO to LUMO is decreases because these are the different orbitals which are participating in the particular transitions. In this structure, this is the structure of lycopene. Lycopene is a carotenoid which is responsible for the red color of tomato. In lycopene, only the absorbing unit is carbon-carbon double bond. And according to basic principle, carbon-carbon double bond shows absorption in normal UV region. But since in the structure of lycopene, there are 11 conjugated double bonds. 11 double bonds which are present in the conjugation. That's why for every one conjugated double bond, approximately there is increase of 30 to 40 nanometer. That's why this compound shows absorption in the visible region. This graph shows comparison between different compounds. These are the absorption spectra of 3 compounds. First compound in which 3 double bonds are conjugated. This compound in which 4 double bonds are conjugated, and this spectra is of compounds in which 5 double bonds are conjugated. You can see in this graph, as the number of conjugated double bonds increases, the value of lambda max at x-axis for a particular bond is increases, as well as the intensity of the band for 3 conjugated double bond, for 4 conjugated double bond, and for 5 conjugated double bonds. It is continuously increases. It means for alkenes, as the number of conjugated double bonds increases, there is a continuous increase in the value of epsilon max and lambda max. Another example of conjugation is polycyclic aromatic hydrocarbons, naphthalene, anthracene, and tetrazene. In naphthalene, 2 benzene rings are condensed. There are 5 double bonds in conjugation. In anthracene, 7 double bonds are in conjugation. In tetrazene, 9 double bonds are in conjugation. Again, as the number of condensed rings or benzene rings or the conjugated double bonds increases, the value of lambda max shifted towards the higher value. So the main application of the UV visible spectroscopy for the detection of unsaturation and conjugation present in the molecule on the basis of pi to pi antibonding transitions. Thanks.